Hello everyone, my name is Johar and we are going to discuss about buffers in this session. It is a micro session. We will discuss everything in briefly. So in this session we will discuss about buffers and what are acids and bases and what is pH and what is meant by pH, how to measure the pH, especially the Henderson-Hasselbalch equation, and what are the different buffering systems in our body and how exactly the buffer system works, and what are alkalosis and acidosis, because the most important thing, that is the clinical significance of knowing buffers and pH in our body, that it is the alkalosis and acidosis. So by definition, buffers are any buffer may be defined as a solution which resists or which does not allow to change the pH of the solution, which might be expected if we add an acid or a base to the solution. So anything that does not allow, we can say does not allow to change the pH of the solution. So let's assume if the pH of the solution is 6, even if we add any acid, it will not go down, or any base, it will not go up. So the remaining pH or the resultant pH will always be the same. But there is a limit to everything, and how we are going to know that what is the limit of that buffer to allow or to does not allow or to resist the change, that is by measuring the buffering capacity. The buffering capacity of a buffer is the number of grams of a strong acid or alkali, that is the base, which is necessary for a change in pH of 1 unit of 1 liter of buffer solution. So if we are adding acids and any other base to a buffer solution, after some time, while adding a lot of buffer or a lot of acids and the alkali in the buffer solution, there will be a change in the pH, and we have to measure how much of the acid or the base will bring the change. That is the buffering capacity. So in exact words, the number of grams of strong acids or a base which is necessary for a change in pH of 1 unit of 1 liter of buffer solution. Now we are going to discuss about acids. I think everybody is acquainted with the acid and base. However, just for the to fresh the memory, it's important to discuss about these terminologies. An acid is defined as a substance, ion, molecule, or a particle that yields or donates hydrogen plus ions or protons in a solution. So, for example, like hydrochloric acid, HCl, in a solution, it will become ionized like this, H plus and chloride minus. So this is the proton. In a solution, usually acids get ionized and it will donate a proton. However, a base is anything that combines with hydrogen plus ions or a proton. So it is exactly opposite of an acid. For example, carbonic acid, this is hydrogen carbonate, or you can say carbonic acid, on dissociation will yield hydrogen ion and bicarbonate ions. The anionic part is the bicarbonate ion. It is a base because it will accept the hydrogen ion, and carbonic acid is an acid because it will donate the hydrogen ion. So like this, the reaction, carbonic acid will in turn become hydrogen proton and a bicarbonate ion, and this is an acid and this is a proton and this is a base. So a base, by definition, base will accept a proton, so this becomes a base, and by definition acid will donate a proton. So in a solution, carbonic acid will be ionized into a proton and a base. However, when the bicarbonate ion combines with proton, it will become an acid. Now, there are many examples of acids and bases in our surroundings. I just mention a few just for the knowledge. So there are many. This is the pH mentioned. As we go to the lower pH, stronger will be the acid, and as we go to the higher pH, stronger will be the base, and the 7 is the neutral. So above 7 is basically the alkaline pH or the basic pH, and below 7 is the acidic pH. In the acidic pH, as we go down like 6, 5, 4, 3, 3, 2, 1, the acid becomes stronger and stronger going on. However, in case of base, as we go up 8, 9, 10, 11, 12, 13, 14, the base will become stronger and stronger. Like for example, the pure water has a pH of 7, that is the neutral pH. In the seawater, it is a slightly alkaline, that is the 8. The urine is slightly acidic, that is 6, and so on. However, there are many things we used in our homes or in our surroundings, that is the drain cleaner, bleach, they are highly basic, and there is a battery acid and the stomach acid, these are highly acidic. So next is the different kinds of acids and bases produced or present in our body, like for example the carbonic acid, sulfuric acid, phosphoric acid, and there are certain organic acids like pyruvic acid, lactic acid, acetoacetic acid, and beta-hydroxybutyric acid. These are also known as ketones. Iatrogenic acids, certain drugs act as an acid when they will injected in the body, and certain bases like nitrogenous bases of the nucleic acids, DNA and RNA. Now we have to know how we can measure the strength of an acid or base. There is a thing, but we call it a pH. pH is nothing but P is meant for the power of exponent and H is meant for the hydrogen ion concentration. So it is basically the inverse log of hydrogen ion concentration. As we had discussed in the last slide, that increase in pH is meaning base and decrease in pH and meaning acidic. Neutral is the 7. More than 7 is base and less than 7 is acid. A pH can be measured by using various methods. For example, the first of all, a general method is by using litmus paper. However, it is not very accurate, but it gives an idea. So what is the principle? Basically, the blue litmus paper will turn red in an acidic solution, and the red litmus paper will turn blue in an basic solution. And there is a universal pH paper, because usually it is khaki color or golden yellow. So when we put in a basic solution, it will turn blue, and when we put in an acidic solution, it will turn red. However, this kind of measurement of pH is not very accurate, but it gives an idea that whether the solution is acidic or basic, and we can use this standard color to analyze how strong our solution. Now the next is next method is by using pH meters in the laboratory. This is the structure of pH meter. Here is an electrode. This electrode is very specific for measuring hydrogen ion concentration in the solution, and then we can calculate, or usually it automatically gives the reading here. However, there are certain things required to maintain this instrument, and nowadays we do not use it in the hospital. We use the ABG machine, which has got several of such kind of electrodes, and each electrode is specific for certain kind of analyte, like for example sodium, potassium, hydrogen, and so on. And the third method is by using the Henderson-Hasselbalch equation. As we will discuss, this is the equation, that is the pH of a solution is equal to the dissociation constant of an acid and the log of the ratio of base concentration and acid concentration. So this is an important equation. We will discuss a little bit more in the future slides. Now in hospital usually we use ABG machines, that is arterial blood gas analyzer, by using ion selective electrodes technology. Each electrode is very, very specific for certain kind of ions, by which you can measure the hydrogen plus ion or chloride ion or potassium ion or sodium ion. So these ions will be measured specifically and accurately by using ion selective electrode. There are electrodes that are very selective for certain kind of ions. So now Henderson-Hasselbalch equation. In this equation, if you see, if this is HA is an acid, in a solution it will dissociate into proton and a base, as we had discussed initially. So the pH of the solution will be the dissociation constant of this acid in a solution, how fast it is being dissociated. And a strong acid will be completely dissociated. However, a weak acid will be only partially dissociated in a solution. So the dissociation constant will tell us how fast an acid can be dissociated in a solution. So higher the dissociation constant, stronger will be the acid. But here we are using basically pKa. pKa is the pH at which half of the acid gets ionized. It is basically the pH at which half of the acid gets ionized. Now the another is the log of the concentration of base over concentration of acid. So we will use this equation. It is and in this slide we are just having acquainted with this equation. Now there are certain examples of buffer in the body. What are exactly buffer, or what are the constituents or composition of the buffer? So the most important thing, a buffer must have a weak acid. As we had discussed in the last slide, that weak acid takes time for dissociation, or dissociated partially only, or very little. Majority of the weak acid present in a solution in undissociated form, and the other is the corresponding salt. So here is the corresponding salt, and here is the acid. This is a carbonic acid, and this is a soda bicarb, that is the base corresponding salt of the carbonic acid. So the combination of this is an buffer. Exactly here, disodium hydrogen phosphate is a base and sodium dihydrogen phosphate is an acid. So this is a combination of this combination, we call it a buffer. In the extracellular fluid, there are three major buffers in our body. One is the bicarbonate buffer system, the other is the phosphate buffer system, and the third is the protein buffer system. Usually it is maintained by the albumin. As we know, in the serum or the blood or the plasma, the major protein is the albumin. In the intercellular compartment, however, the most important buffer is the phosphate buffer, and the second most important is the protein buffer. There are various kind of protein present inside the cell that acts as a buffer. We will discuss in the last slide how the protein acts as a buffer, and there is a bicarbonate buffer as well, but the contribution is very little in the intercellular medium. In the erythrocyte, there is a slight difference. The hemoglobin, since it is the major protein in erythrocyte, becomes the major contributing buffer, and thus phosphate buffer is getting the second place, and the third is the bicarbonate buffer. So now we are going to discuss about how exactly they work. This is the most important topic in this let's suppose we take an example of bicarbonate. So in the bicarbonate there is a weak acid. Weak acid is carbonic acid, and we know that it can be dissociated into H plus, that is the proton, plus bicarbonate ion, that is the base, and the another is the salt, and we know that salt is the soda bicarb, and upon dissociation it will also make like this sodium ion and bicarbonate ion. So what happens? So this is a combination, exactly this is a combination of a buffer solution. Only carbonic acid cannot act as a buffer. It must have a salt, corresponding salt, to be called as a buffer. So weak acid plus its corresponding salt will act as a buffer or a buffering system. So now let's suppose if we add a strong acid, let's suppose we add a hydrochloric acid, it will get dissociated into proton plus chloride ion, and since it is a strong acid it will be completely dissociated. So what will happen when it will be dissociated? Let's write here actually. Like hydrochloric acid will be dissociated into chloride and proton. So this bicarbonate ion and this hydrochloric acid, this proton will get combined and become a bicarbonate or carbonic acid. So the hydrogen ion concentration of the solution will remain the same. This is our main purpose actually, because if the hydrogen ion concentration will increase, it will decrease the pH and the solution become more acidic. Or in case if hydrogen ion concentration gets decreased, it will increase the pH and it will be more basic. So here the purpose of buffer is to maintain the concentration of hydrogen ion, a stable concentration of hydrogen. It doesn't allow to change the concentration of hydrogen ion. So whenever an acid is added or a strong acid, it gets dissociated into a proton and a corresponding ion and this corresponding base, and this proton will get bonded with this bicarbonate ion, so and it will become carbonic acid. So ultimately there won't be any change in this hydrogen ion concentration. The proton concentration of the solution will remain same, therefore there is no change in the pH and pH will remain the same. Now let's suppose, as we had discussed here about the acid, now let's suppose we will discuss about the base. So what will happen if we add a base here? Let's suppose we add an sodium hydroxide. It is a strong base. When we add it, what will happen? There will be a hydroxyl ion and a sodium ion. It will be completely dissociated into hydroxyl ion and sodium ion. This hydroxyl ion will get bounded with the hydrogen ion and make water. Now what will happen as we are seeing this hydrogen gets utilized? So what will happen? So there will be decrease in hydrogen ion and there will be increase in pH, but that doesn't happen in fact, since as we discussed it is a weak acid, only it is partially dissociated, only a small portion. Let's suppose out of 10 only 1 or 2 are being dissociated into proton and bicarbonate ion. The remaining 7, 8, 9 or you can say 90% is remain in the carbonic acid, like this H2CO3 presentation, undissociated form. So whenever the hydrogen gets utilized or in certain reaction or certain neutralizing reaction of a base, some of the carbonic acid will get dissociated and produce the proton. So the concentration of hydrogen ion will remain constant or will remain same. So I hope you understand this situation, how the weak acid will resist any change in the hydroxyl ion as well as hydrogen ion. So the ultimate concentration, the outcome, the final concentration of the hydrogen ion will remain the same. It will not change. Now let's see another example, because this is an example of weak acid and its corresponding salt. The another example will be a weak base and its corresponding salt. So the weak base and corresponding salt situation is we are discussing a little bit different. That is not present, as we have discussed. This isn't present in the body, but it is not present in the body, or present in a body in very minor influence in the body. So the weak base is ammonium hydroxide, that is NH4OH, ammonium hydroxide, and it will be dissociated. Since it is a weak base, it will only be partially dissociated. So it will be dissociated into H4 plus ammonium ion and hydroxyl ion, OH minus. Its corresponding salt will be ammonium chloride, N4Cl. So it will be dissociated like ammonium ion plus chloride ion. So this is basically a buffer solution. This is an ammonium buffer solution, ammonium hydroxide buffer solution. Now let's suppose we add an acid in this. So what will happen? Let's suppose we add hydrogen chloride or HCl in this. So what will happen if we add HCl? This will be dissociated into H plus proton plus chloride. So this will gets combined and it will make the water. However, some of the ammonium hydroxide will become dissociated and the hydroxyl ion concentration will remain the same. Now another example where the strong base is added, sodium hydroxide. So what will happen? It will be dissociated into OH minus plus sodium. So here the ammonium ion will get combined with the hydroxyl ion and will become ammonium hydroxide. So finally the OH minus or H plus concentration will remain the same. In case of a weak acid buffer, it is the main purpose of maintaining the proton concentration constant. Here the concentration of hydroxyl ion, it is the reversal actually. So the ultimate outcome is the constant concentration of hydronium ion is present in the buffer solution. So now just to summarize this, whatever we had discussed, it is the mechanism of action of buffers, how buffer act, and it is an important topic because this is the most important thing in a buffer, how they act, how they resist changes, and how it does not allow to change the pH of a solution if we add an acid or base. So just for the summary, here it is the acid and this is the this is the weak acid and this is the corresponding salt of the acid. And when we add an acid, it will add a hydrogen ion into the solution, and that hydrogen ion will get neutralized by the base. And then when the hydroxyl ion is added, the hydroxyl ion will get neutralized by the hydrogen ion or the proton itself. So this is the summary of buffer, mechanism of action of buffer, how exactly the buffer system works. Now we will discuss about the different buffer systems in our body. As we had discussed already, or enumerated so far, there are many different buffer system in the body. So
This is these are the major buffer systems in our body. One is the bicarbonate buffer system, phosphate buffer system, and protein buffer system. As we see, the table mentioned this is an intracellular and this is an extracellular. And in the intracellular, the acid components is this, and acid component is this, and corresponding salt is this. And in the extracellular, the acidic component is this, and weak acid, this is the weak acid, this is the corresponding salt, exactly like this. So let's discuss about individual buffer systems like phosphate buffer systems and bicarbonate buffer systems. For example, bicarbonate buffer systems, it is the most important buffer system in the plasma or in the blood. 65% of the buffering capacity of the plasma is because of this buffer systems, and 40% of the buffer system of the entire body. So it is one of the most important buffer systems in our body, the bicarbonate buffer system. And we have discussed in the mechanism of action how it works. The conjugate base is bicarbonate ion and is regulated by the kidney, that is, it is excreted by the kidney. So if we are taking, let's suppose if more and more proton is being generated by some acid in the body, then more and more bicarbonate ion will be generated. The acidic part is under respiratory regulation. It means the carbon dioxide, because we know that carbon dioxide plus water will make a carbonic acid. So if there is a more carbon dioxide, there will be more carbonic acid. Okay. So carbon dioxide can be exhaled in the breath by the lungs, and that is under respiratory control. So the acidic part, that is the acidic part, when the acid, since if there is less carbon dioxide, less acid will be there, so more carbon dioxide will be washed out from the body by breathing, by expiration. Now there is some calculation we have to do as per the Henderson-Hasselbalch equation. There are certain information given here, that is the normal concentration of bicarbonate ion is 24 millimoles, and partial pressure of carbon dioxide is 40 mm of mercury, and concentration of carbonic acid is 1.2 millimoles, and solubility constant of carbon dioxide is 0.03, and dissociation constant of carbonic acid is 6.1. So as we know that the pH of a solution, we can calculate like pKa plus log base divided by acid. This is the equation, that is the Henderson-Hasselbalch equation. We had discussed already in the previous slide. So how the pH will be calculated here? If we see, this is the concentration of the base and this is the concentration of the acid. So put it, and this is the dissociation constant. So put it like this, 6.1 plus log concentration of the base divided by concentration of the acid. So it will become 20. Log 10 is 1, as we know that log 10 is 1, and log 2 is 0.3. So just put 0.3 here, 0.3 into 1, 6.1 plus 1 plus 0.3, so it will become 7.4. So this is the pH. So it is let me again do this calculation, so there will be no more confusion. We know that this is the equation by which we are going to know what is the pH of the solution. In this equation we need three things. One is the pKa, that is the dissociation constant. This is the pKa, and that is 6.1. So we just put it here, 6.1. Now log the concentration of the base, and this is the base, this is the base. So the concentration of base is 24 millimoles divided by the concentration of acid. This is an acid. Now the concentration of acid is 1.2. So we just make this like log 20 6.1 plus log 10 plus log 2. We know that value of the log 10 is 1 and value of log 2 is 0.3. It is mentioned on the next slide. So the overall calculation of this 6.1 plus 1 is 7.1 plus 7.4. So this is the pH of the solution if these are the informations given to us. Now in another, why these two are given. Now let's discuss these two as well. As we know, the equation, as in Henderson has a back equation. So the Henderson has a back equation said pH is equal to pKa plus log base over acid. Now here, if you see, if we do not give this information to you, let's suppose we do not give information to you, so how can you know the concentration of an acid? If we are giving these for information only, you can use these two information to get the concentration of acid. We know that carbonic acid can only be formed by water and carbon dioxide. If we had given you the concentration of carbon dioxide and its solubility into the water, you can calculate the concentration of the acid. So here it is, the concentration of carbonic acid equal to solubility constant, how much it is soluble, constant of carbon dioxide, how much it is soluble, multiplied by concentration of carbon dioxide. So it will be, solubility constant is 0.03 multiplied by, and the concentration is 40, so it will be on 1.2. So concentration is exactly the same when we calculate it. So now we put the same thing in the equation as we had done previously. So everything will be calculated and we can get the pH of the solution. So that's how we calculate the pH of a buffer solution. Now we are going to discuss about another buffering system, that is the phosphate buffer system in the body. However, it is not the major buffer system in the extracellular medium. It is one of the most important system in the intracellular. However, inside the cell, it is the phosphate buffer. It is the protein buffer that has the major working. So these are the informations that is required. If the pH is more than 7.45, it is known as alkalosis, because there is a more base present in the blood. If the pH of the blood is less than 7.35, it is acidosis. It means the pH is less than the required. We know that the normal pH of the blood is this 7.4 plus minus 0.02. So it will be around 7.38 to 7.42. This is the pH of the blood. And anything above and below will be considered as an abnormality. However, by definition, if it is more than 7.45, we call it a alkalosis, and if it is less than 7.35, we call it an acidosis, and we have to correct it by giving a base from outside or giving a weak acid from outside to neutralize these things. Now another buffer system is the phosphate buffer system, mainly an intracellular buffer. pH value is 6.8. Ratio of this base versus acid is 4. It is already given. Calculate pH using Henderson-Hasselbalch equation, and the log 4 is 0.6. Now we know that the pH is equal to pKa as per the equation plus log base over acid. We know this is the base, this is the acid. So base over acid concentration is already given. So the pKa is 6.8. 6.8 plus log 4. So 6.8 log 4 is 0.6. So it is 7.4. So again, the value comes as 7.4, and we know this is the normal value of our blood pH. protein buffer system, exactly the same manner the protein buffer system works. Here, this is the acidic part. It is a weak acid.
Hi there, what's up?
It is a weak acid, and it is a corresponding salt. And we have discussed how what is the mechanism of action of the buffer system. And hemoglobin in red cells, the buffering capacity of the hemoglobin as any protein depends on the number of dissociable buffering groups. These are the different buffering groups. One is the carboxylic acid group, this is the amine group, basic guanidino group, and imidazole group. Imidazole group is very important in as far as the hemoglobin is concerned. Why? Because it is present on the histidine, and it is one of the most important contributing factor that leads to the buffering system of the hemoglobin in the RBCs. With the pH range of 7 to 7, most of the physiological buffering action of hemoglobin is due to the imidazole group of amino acid, histidine. Each molecule of our hemoglobin contains 38 moles of histidine, so there is a large quantity of histidine present in hemoglobin. In alpha chain, histidine is 87 position, and in beta chain it is in 92 position. Is directly linked with the ion of ferrous ion or heme. So this is all about buffering systems as well as buffers and what is alkalosis and acidosis. A detailed lecture will go on online, inshallah. And have a nice day. Please stay safe. Thank you very much.